I'll just wait for the recording to start. Let's see. Okay. Okay. So basically, I'll be no, I think that's not a good idea. Okay, so can you see the slide on the right hand side? The slide means I hope you can see the entire screen. On the left hand side is a pane with a video which I'll be playing later on. But on the right hand side, basically, there is the title slide. Can you see the slide and hear me, of
Yes, ma'am.
course? Okay. So this is, experiment number 8 that we are about to study, the study of speed control of DC servo, right? So it was supposed to be done in the control systems laboratory, but anyway, we'll have to do it this way. So the objective first, right? So in case you, want me to repeat something or do not understand something, you can always let me know then and there, or you can ask your questions at the end, whichever way, I don't mind, because it is going to be about more than an hour. So basically, you can interrupt me, no problem. The objective is to configure closed loop speed control system using standard servo system blocks and to study its stiffness against load torque. So that is the objective of the experiment. And I'll just first of all show you the block diagram as in your instruction sheet. So I'm sure all of you have got the soft copy of the instruction sheet. Have you? Have you got the soft copy of the instruction sheet?
Yes,
Yes,
ma'am.
ma'am. Yes. So that's available with you. You need not really note down anything from this unless you want to note down what I'm saying. That's different. So now over here you find that this is the block diagram which is already given in your instruction sheet, right? So you find that there is an input port on this side and then an amplifier unit, PID controller, pre-amplifier, the servo amplifier, and then you have the servo motor over here, DC servo motor in the field controlled mode, as you can see. Sorry, it's not field control. You can see the field over here. Okay, so basically it's the armature controlled mode. So you can see F1, F2 are the terminals of the field, A1, A2 are the armature terminals, and it's in the armature controlled mode. And the field will be excited by using a constant field current, that is. And then you can also see the armature being coupled with the tachogenerator unit, and then the brake over here, and the feedback. So I'll go to each of these units in details in a moment, right? So first of all, photograph of the laboratory setup, right? So this is what you would have seen. In fact, your batch has not done the third year experiment as well in this lab, isn't it? So you did not do it, right? So you may not have seen this. Maybe in your second years when you visited the lab, you may have seen this unit somewhere at the corner of the control systems lab. But this is what it looks like actually. There are several units. These are separate units that you see. I'll go to each of these units and explain what they stand for and what they are used for in a moment, right? So basically, by connecting these in the configuration shown in the block diagram, we would have performed the experiment, right? So now coming to the details of the units. So over here in this particular photograph over here, you find this unit. I hope you can see the cursor, right? So this unit over here is redrawn. You can see that light blue color arrow showing you that unit with a closer view, right? So you can see the name of the block. Name of the block means there is a code name that is given. This left hand side feedback is basically the name of the company, Feedback UK, who has supplied the unit to us, and this is the name of the block code that they have given. So each of these are going to have different codes over here. You can see that it's a power supply. It's written over there, right? So in the power supply, you will find that there is something like this, an indicator, which is going to show you exactly what the value is as such for the current. And you have the switch over here, which can be switched either to the 0 position or the 1 position, meaning that it can be on or off, right? And you also find that there are several terminals over here. So you can see rather that here there are 3 terminals, plus 15 volts, 0 volts, and minus 15 volts. Obviously, the 0 volt is the ground, right? That is one option. you can connect your units to these three terminals if you so require a voltage between plus 15 and minus 15 volts, right? You can also see, I mean, there are other, I mean, options available. So 0 to 18 volts AC, and then you can see others. I mean, over here again another minus 15, plus 15 to 0 and minus 15 on this side. So it's obvious, but this is a closer view of the power supply unit. Similarly, we'll have a look at all the units or the ones that we will be requiring. So next we come to the unit on this side, that is these are the input and output ports, right? So a closer view of the input port and the output port are shown over here. So the input port is actually, I mean, if you rather if you look at the if you look at the unit, you will see something like this drawn, right? This one, the input potentiometer, you can see the name is given over there, name or code, whatever you call it. So there is a, you can see two terminals, 1 and 2 over there, and the 0 volt, and then the output side can be tapped from this screen over here. Now this unit, the connection wise, is shown over here on the right hand side. So this and this are the same thing. You can see that 1 and 2 are two ends of the, I mean, they would be connected to the input side. You can see the input side will come over there, and the your tapping means the pointer is going to be taken from the your from end number or terminal number 3. So you can connect the output side either over here or there. The output is going to go from there, I mean, right? Similarly, there is also another unit, that is the output potentiometer. Both the output and input potentiometers are similar units, but two of them are present over here, because when we use the configuration of the closed loop one, we will be requiring the two ports simultaneously. So this is also similar in configuration. I mean, as far as your as far as the terminals are concerned, right? The only difference you would see is that there's 0 volt is missing over here. But anyway, so here again you have the connection diagram on the right hand side. Next, we have something which is known as the attenuator unit. So the unit is actually this one, which is shown, the closer view is shown, where you find that here there are markings over here like a dial, right? Two of those over here. So basically, according to the, I mean, the indicator is going to be pointing towards one of these, depending on, I mean, what value you want, and accordingly you will be getting the, I mean, you will be getting the value, right? So basically, these are sort of dials which are going to give you uh, the option of changing the position of the ports actually. Next, you have the op-amp unit. So it's shown over here, this one, this unit that you see in the photograph, which is shown close up over here is shown, and the corresponding circuit diagram wise, it is shown over here. Now, here you find that this is the op-amp. You find the negative sign over there, minus A, means that it is an inverting op-amp, right? And then the input side would be these 1, 2, 3 terminals over here, and you find that this I mean, you have the option of putting in the supply over here as well, and the output will be tapped from either here or there. So the connection is shown over here. So you can see that these are the input side is coming over here. The output will be tapped out from there, provision for power supply over here. So we'll see the connections, how these are connected in a moment, but before that, the units will be completing. Next, we have a PID controller unit, right? So PID 150Y is the name of that unit. I'll be explaining what these terminals as well as switches do in a moment, meaning later in a bit more of detail as far as the PID unit is concerned. Next, we have the pre-amplifier unit, right? So pre-amplifier again is another stage of amplification as such. And so you find that this is what it looks like, whereas you see that it is an amplifier that's shown over there. So two signals can be applied at the input side and the two can be tapped out from there. Next, you have what we call the servo amplifier unit. So this block is marked over here in red on setup, and this is what it looks like, the right hand side diagram. So over here now you find that this is the your, first of all, the name over here, and you this is again an amplifier, so it would be performing the task of one more stage of amplification. Next we have this unit over here. So these are three units that are shown. This one, the red box one, is shown over here. That is the DC motor. You can see it's drawn over here, right? So the armature terminals are actually shown, right? And then you have this unit, which is the brake unit. The green box over here, I hope you can see the color, is shown in details over here. Basically, this is the load unit, right? Or the braking unit, BRAKING, as it is spelled, right? So here, basically, we'll be seeing the video in the video how the position is changed. Basically, by changing the position of the load over here, the load amount of load is the value of the load is actually controlled, or rather it's changed, right? So there are markings over here in the load unit, and according to the marking that you set it at, a load will be applied at the shaft. This is the shaft, right? There is a mechanical coupling between this DC motor unit and the right hand side unit, which you actually see over here, which is the tacho unit. So basically this is the tacho unit from which when we are doing the closed loop configuration, we'll be taking the feedback. Now the instruction sheet is already available with you. I'm not reading out what exactly is written over there, and just a printout of that is given over here, and then this one, and finally this one, right? Now this is the sheet in your instruction sheet, the report. Now I will be, after this I'll be showing you how the connections are done, a bit of details of the PID unit. Then finally I'll give you a handwritten copy of the results which you would have got for run 1 and run 2 of this experiment. Now based on those, the sheet, that is the data sheet that I give you. Give you means I show you over here, and then I'll actually be just emailing that particular sheet to you so that you can have a look at it, because it may not be possible to note down from the screen like that. So I'll be just emailing that particular sheet which has the experimental data, from which you would have to complete the report and then email it back to me. Okay, so that is the way it is going to be done. You will be marked on your the report that you send back to me. That is to be done preferably within a week, right? By next Friday would be, not this Friday, but the next Friday would be a good deadline to follow. So, you have on this sheet written what you are supposed to do for the report. So now I will be starting the video. Video 1, okay, yes, and correspondingly I will be actually narrating what is being done in the video. I'll be stopping the video bit by bit after a bit is done, and then telling you the details that were shown over there, right? So I'm playing the video, but I'll be stopping it. The corresponding narration is given over here. I'll be saying the same thing or similar things in a bit more of details. Okay. So I'm starting the video. So first what will be done is that we will be powering up the respective units. Whichever unit requires the power, those things will be powered up. Now, the first unit that is being shown over here, this unit that is being touched, this is the op amp unit. So you see that it is written over there, right? So that is the op amp unit. Okay. So, okay, so these are the input terminals that are being pointed to, right? So this one and this one, right? And there are three, I mean, terminals over there which can, I mean, act as the terminals for adding the signals. Uh, Let me see if there's some latecomer who has come. Is it? No. So, right, so it can add up to 3 signals. Right, so now you see that a connection has been made from this input port to the input of the op amp unit, right? So the connection has been shown over here. The corresponding connection has been shown over here with the red line. You see that this is the input port unit. I hope again that you can see my cursor. This is the input port unit, the output of which basically is connected to the input of your op amp unit, right? So this is being the input port has been connected to the op amp, right? So that is what the connection over here that is shown. Okay, so the next thing that has to be done is that, okay, so the output of this potentiometer has been connected to the op amp, but what has to be done is this input side of the potentiometer has to be connected to the power supply. Okay, so that is what will be done next. Let's see. Okay, so one terminal has to be connected to the plus 15 volts of the power supply unit. The other terminal, we'll see, is connected to the, let's see. Okay, so okay, so this terminal has been connected to the 0 volts. So that means that 0 volts to 15 volts plus 15 volts, that is a range of 15 volts has been applied to the input side. So if I look at this diagram, basically 0 to 15 volts has been applied. The input side range is 0 to 15 volts. Of course, the output tapping will depend on my attenuator unit. When I mean change the dial over there, basically the value of the output side will be changing, right? So so that now he has pointed to the output of the op amp unit, which is this one over here in our diagram, this side. Okay, so the output of the op amp, let us see the connection first. So as per our, okay, let me change this slide. Okay, so okay, power has to be applied to the potentiometer input terminals that we've already done. One input is connected to the plus 15 volts from the power supply in the servo amplifier unit, and the other is connected to the ground from the servo amplifier unit. So basically, what has been done over here is that the powering up of the potentiometer has been done from the from the power supply that is, I mean, there in the servo amplifier unit. Basically, there are 2 units you can see over here. This is the power supply unit, which is internally connected to the servo amplifier unit. So in the servo amplifier unit itself, there is a provision from where you can tap the power supply, and that power supply actually has been tapped for powering up the input port. So that is the portion that has already been done. You can see that written over here, right? So from the servo amplifier, the connection has been given. This is the connection that has already been done. So plus 15 volts one of the terminals and 0 volts to the other terminal, which makes it a range of, as I told you, 0 to plus 15 volts on this side, right? So now, I mean, we've already connected the output of this input port to the amplifier unit. Let us see what is done next, right? So the output of the op-amp unit, the output of the op-amp unit now, right? So that connection is going to be done next. So basically, the output of the op-amp unit is connected to the servo amplifier. So this is what has been done over here. If you just look at it, this one, right? So this is the connection that is shown in the red over here. The output of the op-amp is connected to the input of the servo amplifier. This is actually as per the block diagram. I have not put the block diagram on every slide, but you can understand that the op-amp will be connected to the servo amplifier unit. That has been done just now. As has already been mentioned, the servo amplifier by itself does not require a separate power supply as such. It is internally connected to the supply. Okay, so the op-amp unit, that is this unit, now will be powered up, right? So that is the connection that has been shown now in the video. Okay, right. So this has been connected to the power supply unit, right? So over here, the op-amp unit, the plus 15 has been connected to the plus 15 volts of the power supply unit, and the minus 15 has been connected to the minus 15 of the power supply unit. So these are the two probes that you see over here. Just now, the connection has been made, right? So let me go to the next slide. Yes, and again, the 0 volts now. Right. So that is, I mean, on the in the video you find now there is the powering up of the op-amp unit has been completed. So correspondingly now over here you find a clearer diagram where you find that the op-amp unit is being powered up from the power supply unit respectively from the plus 15 volt to the plus 15, 0 volt to 0 volt, and minus 15 to minus 15 volts, right? That is what has been just shown. So these are the probes which are being referred to over here, right? Going to the next portion, narration 4. Yes. So the servo amplifier is internally connected to the motor unit as well. Okay. Right. So no other connection has from the your servo amplifier unit to the motor unit, which is internally already present, right? So that completes the forward path of your block diagram, right? So next, what is being done is a multimeter will be used. Let us see. Right. So multimeter is used to measure the tachogenerator voltage. So one end is to be connected to the terminal of the tachogenerator unit is going to be connected to the terminal of the multimeter, and the other end to the ground of the multimeter, and also to the ground of the power supply. So that is the connection that is going to be shown now. Let's see. Okay, so this is the tachogenerator unit that he's connecting it to. So the multimeter, yes. So one end is being connected now, and so the other end is grounded to, I mean, connected to the ground of the multimeter, as well as it will be separately grounded. So now ground, it has been this one, again, has been connected to the ground of the power supply unit as well, right? So that grounds it. Okay, right. So that completes the, I mean, the open loop connection, meaning that this, just to see what is happening. So, okay. So just to mention certain things, you see over here that the person is actually holding this unit. This is the brake unit or the load unit, right? And the load unit will be actually, I mean, it will be sort of changed. The position will be changed, and accordingly, the load is going to be, load on the motor is going to be changing, right? So basically, that is going to be shown over here. The power is has been switched on. Actually, you can see that the motor is rotating, and here also you can see the rotation, right? These are the brake positions. So I mean, you find that here there is, it's not visible, but there are markings over here. So zero position over here means that there is no load. On the other hand, there are settings like 2, 4, 6, 8, 10 over here, and accordingly the load is increased. So I mean, if this is sort of rotated such that the pointer points towards position number 2, then it means that some load has been applied, and then the load can be gradually increased depending on what load you want to apply. Okay, so the brake position can be adjusted. Zero brake position means that there is no load. As the load is increased, the speed will be reduced. So this can be read from the tachogenerator voltage. So basically the multimeter is reading the tachogenerator voltage, and I mean, by changing the load, meaning by increasing the load, you can see that actually the speed of the motor will be reduced. So that can be read from here. So let's see. So this is the load is being applied, it's being increased over here. Okay, so you can read the current from that black, this multimeter, as well as the voltage from there. Okay, you can actually see that when he's taking out, I mean, sort of taking the load into this position, it means that zero load is being applied. You'll see that the rotation of this is increasing, whereas when this is being taken closer, meaning some load is being applied or load is being increased rather, you will find that the rotation over here is, the speed of rotation is decreasing. You can see that this is a no load condition. Okay. Over here, again, this is the multimeter from which the tachogenerator voltage can be read. So let me go to the next slide. Okay, we'll come to the this one. Okay, so as you can see, when the load is being applied, this rotation, I'll put on the video, you'll see the rotation has, the speed of rotation has reduced, right? So that's obvious. No load condition, it's going to rotate much faster. Okay, what is being done is that the input side voltage, that is this side, is being changed. Changed meaning that if it is made almost zero, input voltage is made almost zero, we'll see that the motor will almost stop. So that is what we'll see next. Okay, so this attenuator unit, I don't know whether it's visible. The attenuator unit is what you have over here. And depending on whether you increase or decrease the input side voltage, this rotation of the motor will be changing, increasing or decreasing, depending on the load, right? So as the input side voltage is increased, the speed of the motor increases. So the input port, actually this side, that is the attenuator unit on the input port, can actually be changed, and accordingly the speed of the motor can be controlled by changing the position. Increasing or decreasing the value over here on this side, on this dial, will be changing the speed. Okay, so now coming to the values as such, values meaning readings. Okay, So now what will be done is that next, I mean, this op-amp unit, as I told you, it is an inverting amplifier, right? So basically, I mean, the whatever you apply, whatever voltage you apply on the input side, that is going to be inverted, and you will get the inverted voltage on the output side. So that is going to be checked right now. So let us see. Okay. So just putting it back by 2 frames. Basically, what we are trying to do is we will try to see, uh, uh, first of all, the polarity, right? So the polarity should be checked to verify that it has been inverted, right? So initially V1 should be equal to VI, I mean, capital I is what is there. So V at the input side should be 1 volt, right? So we use this multimeter that is being shown over here to measure the VI value. So for that, connect the ground of the multimeter to the ground, and the output of the op-amp unit is measured by connecting it to the multimeter. So that is what is being done now. Let us see. Okay, I'll just put it back by 2 frames so that you can see. Okay, so just just wait. Okay, so now you can see, I mean, this has been, the output of the op-amp unit has been connected to the multimeter, and the ground also will be connected. Ground is being connected to the multimeter unit so that we can actually measure the value of VI. I think we go to the next, sorry, okay. So I think we go to the next video. Next video means it's a continuation of this one itself. Okay, let's just wait. Yes. So now, I mean, what is being done, it's a continuation. So you can see that this is connected to the multimeter. That is, the output of the op-amp unit is connected to the multimeter, and the other terminal of the multimeter has been grounded. So now with that, basically, the value, that is value and polarity mainly, is being checked. Polarity of what? Polarity of the output of the op-amp unit. Because what we require to do is we require to apply a positive voltage to the motor taco unit so that we can take the readings. The readings will be positive. So for that, basically, the polarity of the output of the op-amp is being checked. Okay, so if it is negative, we'll reverse the terminals accordingly and get a positive voltage at the output side. So now over here, if you look at it, okay, so this is VI. We find, okay, can you see that? Ah, it's visible, isn't it? Minus 10.62 is the value that you see over here for this particular thing. So minus means that the output of the op-amp unit as a negative voltage as expected. If we apply a positive voltage, because on the input side, you remember we had applied 0 to plus 15 volts was the range that we applied. So I mean, in all probability over here, the setting is such that about 10 volts is being applied to the input side, thus reversing the polarity, and at the output of the op amp you get a minus 10 point something volts, right? So that is what has been seen over here. So we find that VI is around minus 10.6 volts as per this particular reading over here, right? So we have to apply a positive signal to the motor terminal. So instead of applying plus 15 volts to the input of the pot, we apply a voltage from 0 volts to minus 15 volts to the input of the pot. So that will mean that after inversion, the output of the op amp will be a positive voltage, and that can be applied to the motor. So that will be done next. Let us see the video. So the input of the potentiometer, you would recollect these other terminals had been connected to 0 and plus 15 volts. So it's going to reverse one of those, make it minus 15. Okay, so he's showing that the input side of the op amp has a positive voltage, 11 point something, and the output side has negative. So that's verified, right? So it means that now the input of the input of the potentiometer, the only, as I told you, would be input side. The range should be from, instead of from 0 to plus 15 volts, if we put 0 to minus 15 volts, then we'll get a negative voltage on the input of the op amp. Thus, after reversal or inversion, the output of the op amp will have a positive voltage which can be applied to the motor taco unit. So that reversing will be done now. Okay, so he's just repeating and showing that the output of the op amp is negative voltage, whereas the input side is a positive voltage. Okay. So that plus 15 volts, no, okay, so that has been reversed. So it was connected from 0 volts to plus 15 volts. Now he has switched that terminal to the 0 to minus 15 volts. So that will make a negative voltage at the input of the op amp, thus making a positive voltage at the output of the op amp, and that is going to be applied to the motor taco unit, right? So that inversion has been done. He has switched it on. Yes, so now he's showing that, yes, now there is a positive voltage at the output of the op amp, right? Right. So he's now actually, I mean, changing the input voltage to a particular value, say 1 volt, around 1 volt, and then basically putting the brake. He'll be putting the brake now. The brake position is now put at 10, and that is the full load condition. So you can see as the brake has been applied, the rotation, the speed of rotation, you will see, I mean, provided your connection is good enough, you'll see that the speed of rotation has decreased, right? So again, over here on the, tacho generator side as well, he was, I mean, he has reversed the polarity so as to get a positive voltage at the output side. Okay, so that is as far as these videos are concerned, and that is as far as the basic, I mean, forward path is concerned. So now, I will stop the video. I've already stopped it, in fact, and now we'll see what requires to be done next, right? So you find that you have to note several things. Note the armature current at which the motor starts crawling in either direction. So basically that can be done. You can see that, first of all, I mean, take the motor to the positions, or rather the values for which the motor actually stops, and then slightly increasing the input voltage, you would be able to see when the motor just starts crawling in either direction. You have to note those values, and then, I mean, basically those have to be Yes, those have to be noted down, right? So then gradually increase the speed of the motor till the tacho voltage is 10 volts. So by noting the input voltage, armature voltage, motor current, tacho voltage, and the time for 20 revolutions in the low speed shaft as per the following table, determine you have to, this is the table that we are referring to. To determine the observed speed, tachometer constant, tachometer constant, effective viscous friction, torque, and all that. So basically now I'm not reading out over here from this. So you find that next the different formulae which are to be applied are given over here, and the table in which the notings are to be done is also given in your instruction sheet. So now, the next thing that has to be done is that you find that here, as per the table which is supplied to you, you would have to actually apply, this is the block diagram. In the block diagram, you find that after the op-amp unit, you have to connect the PID controller unit, and then, setting a particular proportional controller gain, you would have to take your readings, right? So now we will go into the details of this unit, that is the PID control unit. Until so far, we have not actually connected this dotted path, that is the feedback has not yet been connected. Apart from that, the rest of it, the forward path, has been fully connected, and I've shown you what exactly is happening, apart from the PID controller unit, of course, which has not been connected. So next, what would have to be done is that the PID controller unit has to be inserted in between the op-amp unit and the preamplifier unit. So basically, instead of directly connecting the op-amp unit to your preamplifier and then the servo amplifier, the preamplifier actually we don't connect over here, but anyway, directly to the servo amplifier. Instead of doing that, the op-amp output will go to the PID controller unit, and from there we connect to the servo amplifier unit. For our experiment, we have not used the preamplifier unit, which is just another stage of amplification, right? So function wise, you have this stage, that is a summing amplifier which amplifies, and then again you have a pre-amplifier unit you may have, that's optional. Then you have the servo amplifier unit. So all these are serving the purpose of amplification. In our particular experimental setup that we have in the control systems lab, we do not connect the pre-amplifier unit separately. We use only the summing amp and the servo amplifier unit, but anyway. So now we'll come to the details of the PID controller unit, without which you would not be able to take the rest of the readings. So the PID unit next. So first of all, this is the unit you can see, right? And you have to apply the power supply to the PID unit separately, right? So you can see the plus 15 volt, 0 volt, and minus 15 volt terminals over here, which have to be respectively connected to the terminals of the power supply unit. So you connect this end to the your plus 15 volts of the power supply unit, this terminal to the 0 volt of the power supply unit, etc. So minus 15 to the minus 15 volts of the power supply unit. So that is the first connection that has to be done as far as the PID controller unit is concerned. Next, we have a closer look at what are present on the panel, the front panel, right? So here we find that there are several switches, this one and this one and this one. You can see those are switches where you have in out written. On each switch you have in out written over there, right? So each in-out switch must be placed appropriately to include or exclude a particular control action. So in means that that control action is included, out means that that control action is excluded, right? So basically, depending on whether you want, say, proportional controller, you will set the corresponding switch to the in position. If you don't want it, you set it to the out position. Similarly, for all the other units, sorry. 30 means actually the units that the switches that I'm referring to are marked with the red arrow over here specifically. So you find 3 of such switches that are marked with in and out. So this one is in out. You can see, you can trace it. It goes to the, this is the proportional controller unit, right? So this switch, when placed in the in position, will include the proportional controller. When it is placed in the out position, it will exclude the proportional controller. Similarly, now the next one that we see, this one is actually connected to the integral controller unit. So this switch, when placed in the in position, will include your integral controller, whereas out will mean that that is excluded. And is third one, this one. So this is the third switch, which is connected to the derivative controller unit. So when this is switched into the in position, it will include the derivative controller. When it's put in the out position, it will exclude the derivative controller, right? Next, we also find another three switches which are marked with a blue arrow. Those are separate. So that actually is this one. That is, the multiplier switches are indicated by the blue arrows. Those are also switches looking similar, but those are multipliers. So the multiplier switches can be used to select the values of the controller gains. So say, for example, this multiplier switch is connected to the proportional controller. So if you switch it to the you see multiplied by 1 multiplied by 10. So basically, if you put it to the 1 position, it means that if the setting over here is 5 units, then your gain is 5, right? If it is or rather, I think I think it's 0.1, 0.2, 0.3, 0.4, 0.5. So 0.5 into 1 will give you a 0.5 kp value, right? Whereas if you switch this multiplier to the 10 position, the 0.5 position over here will indicate 0.5 into 10, which is 5 units for the kp value. Similarly, for the pi and td, you have the option of putting the multiplier switch either into the 1 or the 10th position, which is going to multiply by a factor of either 1 or 10 according to your setting. So for the three blocks, meaning the derivative, the proportional, and the integral, you have three separate multiplier switches. Okay. So when P control or PI control is used, the input should be applied to this particular point, which is called, or I mean, it's marked as the input error point. So this is the point where you would have to make the connection, meaning that, say, for example, if the output of the output of the operational amplifier is coming to your PID controller unit, then the output of the op amp should be connected to this particular point, right? It is called this input error because usually your error signal will be what you are applying over here. So it's actually already called input error, right? So in case you are, using the PID controller unit either in the P mode or in the PI control mode, P control mode or PI control mode, you would be applying the input to this particular point over here. In case you are using the derivative controller as well, you would have to make an additional connection over here. So this unit, derivative unit, has to be directly connected to this point separately, externally, by using another probe from outside, if you want the D controller to be included, right? So in case you are using a proportional controller, this connection is not required. If you are using a PI controller as well, this connection is not required. If you are using a PIT controller, yes, this is also required. If you are using the PD controller, then also this connection would be required, but you have to switch off your integral control unit. So I mean, this integral controller switch will be in the out position, and then you will be having the P and the D, right? So that is the way it works as far as the your unit is concerned. Right. So as I mean, the table is shown over here. A table for taking down the experimental data is shown over here, where you would have to note the error voltage as well, right? So keep the brake at position 2, switch off the power supply, and connect the system as a speed control servo with the proportional gain set to a particular value, 0.2 into 1. So I mean, the PID controller unit, you would have to use it in the proportional control mode and set the value at 0.2 into 1 for the kp value, right? So that means that the integral controller switch has to be set to 0 or not 0, that is in out, so out position. Similarly, derivative unit would be in out position. Only the proportional controller switch would be in the in position. Now you would have to note what is called the error voltage. So error voltage means that you would have to take the output from the op amp. So output of the op amp is what the error voltage is, because this is the summing amplifier. So this point is the point where you are going to get the error from, right? So from there, you will have to connect the multimeter over here and take the readings. Okay, so next, what we have is, okay, I'll try to put it in the slideshow mode so that you can have a look at this, the readings. Though actually I'll be mailing to the common mail ID just one page of this handwritten report where the experimental data is given, but just for your benefit I'm showing it. Is it visible? I hope it's visible, right? If not, just let me know. So here you find that, is it visible? The whole screen should be visible, right?
Yes, ma'am, it
Hmm.
is.
Ah. So this is the run one, that's the open loop one. So by varying the different, I mean, the break position, putting it to 2, 4, 6, 8, 10, you would be having to note this. That is the input voltage VI at the preamplifier, and then the your motor current, armature voltage, and then the your compute the tacho voltage and this and the sorry no, you have to note the tacho voltage and also the time taken for 20 revolutions. So these things are actually going to be supplied to you. The whole of this table you will be getting. Next, this is the closed loop configuration, where now you would have to here it's not visible. This is the first two, that is there are three divisions you can see over here. The first one is for a kp value equal to 0.2, so proportional controller set to 0.2, and then changing the brake positions. You have whoever has done the experiment has actually noted the tacho voltage, motor speed, and the error voltage, right? So, I mean, from there, the rest can be done. So, you actually, for zero point 0.2 and for 0.6 kp value, this has been, tabulation has been done. And for next, what has been done is that PI mode has been used. So, over here, you can see kp is equal to 0.2 and TI is equal to 0.1. So, the error voltage has been also noted. So here from these runs, what you see is, and then the error RPM and the motor current also are there. So basically what you see over here is that by increasing the proportional controller gain, you would have theoretically learned it at some point, maybe the in your PIC, that is process instrumentation or control, or elsewhere. In fact, I think even in the control systems class in the third years, we tell this thing. That is, when the proportional controller gain is increased, when the proportional controller gain is increased, the error basically would be the steady state error is what I'm referring to, basically would be decreasing. So you see 0.2 over here is the proportional controller gain. For a brake setting of 2, you find that the error voltage was 0.28, whereas for a similar brake setting over here for kp equal to 0.6, you find that the error voltage has decreased. So corresponding to each particular brake position, you will see that increase in the proportional controller gain has reduced the error voltage, right? So that is one of the, and I mean consequently the error RPM as well. So that is one of the notings from this.